Sure. All right, can everybody see my screen?
Yep.
Great. All right, so this session is around creating a stack with PySTAC. And PySTAC is a Python project that aims to be a pretty simple, lightweight library for working with stack in Python, right? So we have installation instructions here, and you'll notice that it does have just a single dependency, Python date util. However, if you want to perform some of the validation logic, there's this command to install the extras, which is really just installing one other library, which is JSON schema, has its own dependencies. So you would just pip install here. So what I'm going to navigate to right now is in the documentation. Actually, this will show up in the PySTAC documentation. So the docs documentation is right here, pystac.readthedocs.io. We can go to tutorials and see this new tutorial called creating a Landsat 8 stack. And I'll go ahead and navigate to the GitHub version to start. So GitHub will render the notebook for us, and I'll just be going through this, this today. So the first thing we'll do is start up a Jupyter notebook locally. I'm sorry, the first thing we'll do is actually make sure that PySTAC is installed. So to do so, I'm going to go ahead and work off of my clone of the repository, right? I just did git clone. You can do github.com stack utils PySTAC. That will clone it into the repository, and you can see I have my local clone here. I'm going to go ahead and start a virtual env in order to manage my Python dependencies a little better. If I wanted to start a virtual env, a new one here, I would do something like this, and I've already done this. My virtual env directory is here. So what I'll do is I'll just say source fem bin activate, and then so now I have a virtual environment that I can install Python dependencies into. So I can install PySTAC from PyPy, pip install PySTAC, and then I can include that validation extra to make sure that I have all the requirements for the JSON validation. Also, if I'm inside of a clone of the repository, I can do something like pip install dot validation. That'll also install it directly from the repository. So if you're working with the latest that has unreleased features, you can install like this. And we'll just give that a second. Not sure why that's taking so long, but I'll quit out of it. Oh, there we go. Yeah, we'll try that. So found and existing, we'll just ignore that. So if you have Jupyter installed, you can run a Jupyter notebook but with this command. I'll set the IP equal to 127.0.0.1, just crack on my machine, and set the notebook dir to the current working directory. And that should open up a Jupyter notebook instance with the repository here. So I'm going to go into the docs, into the tutorials, and find that creating a Landsat stack notebook here. Great. So I'm going to go through this notebook, and you know, like you saw, it's available online. So feel free to you know, run through it in your own time. Or if you have everything sort of set up, feel free to follow along. Great. So first thing I'm going to do is I'm going to import PySTAC, and now we'll go ahead and read information about Landsat 8 scene data into our notebook. So there's a set of scene metadata that's in a gzip file hosted on AWS. This is for the collection one information, sort of any new data that is for new images coming in and new back process data exists in the scene list. So we'll go ahead and read this in. It's not a small file, so it'll take a little bit of time, but basically what we're doing is we're just unzipping the contents of this file and then using the Python dict reader to read in that content so that we'll have a list of scenes. And once that finishes running, we'll be able to see how many scenes are contained in that list. This is one of the longer steps, so ideally it doesn't take too long. And so basically in this tutorial, what we're going to be doing is, we're not going to be processing every Landsat scene in this list. That would take a long time. We're going to actually take a subset of the scenes, right? Because there's over 2 million scenes here. And a scene, the metadata that's included in the CSV looks like this. We have the product ID, we have some information about the cloud cover, the location of the scene, and then this download URL. So we're going to use this metadata to filter scenes by a location and by a year. So I just have the latitude and longitude coordinates for Philly, which is where I live, and the year set to 2020. So if you're walking through this notebook now or later, feel free to change this up to your own location. So I define a function here called keep scene that just uses the information in the scene to filter out to make sure that the min and maxes of the coordinates line up, and then also that the filter year is included in the acquisition date. And so now we see that we've got it down to 52, which is a manageable amount. Great. So to start off with this in this notebook, we'll end up processing all 52 of those scenes and turn those into stack items. But for now, let's just start with one. We'll just grab the first scene and start to take, read in information about that and convert it to a stack item. In Landsat that's hosted on AWS, there's a metadata file called an MTL file that is hosted alongside of the index.html. So we're going to use this download URL to grab asset HREFs, asset locations across the board here. So we're going to define a function called getAssetURL that will take a suffix so that we can grab any of the files related to the scene using that method. So we'll get the MTL URL by passing mtl.txt to this, and then we can print it out. And you can see this is a text file, sort of a plain text file that has indentation to organize information, metadata about the scene. Notice here too, I'm using this PySTAC, stack.io read text. This is a method in PySTAC that it uses to read stack information. There's also a write text method. And I'm using it here sort of as a straight utility method that can read from local file or HTTP. There's also documentation around how to modify the stack.io to be able to read from any cloud provider, or just provide custom functionality for reading any sort of storage that can hold text. So to work with this MTL file format is a little tough, but we can just define a function that converts the Landsat MTL file into a dictionary of metadata, which makes it a little bit easier to access the individual key value pairs. So now that we're armed with all this metadata, let's go ahead and try to create a stack item from this scene. So the first thing I'm going to do is look at the required properties of the init method of item. Another thing I can do is just say PyStack.item and then use Jupyter's functionality to sort of see, okay, what do I need to supply to this? I need an ID, geometry, bbox, datetime, and properties. The rest of it is going to be optional. And then so let's start let's start collecting properties or values for each of those properties. So the item ID, pretty easy. I'm just going to use the Landsat scene ID. I'm going to chop off the last 5 bits because they're sort of repeated for every Landsat scene and I don't need it. To get the date time, this is also in the metadata. It's just contained in 2 separate fields. So right now we're just kind of mapping the MTL metadata to STAC metadata. You can see we have a parse date time, and I'm using a datetime Python object to represent the date time because we're working in Python. We want to be able to add dates, compare dates. So instead of working with date strings, we're going to be working with the actual datetime objects. To get the bounding box, right, there's MTL data around the upper left, the lower right, etc., lat and long coordinates for the scene. So we'll use that to get our bounding box for the scene. To get the geometry, this is a little bit more tricky than the bounding box. We actually need data that's contained in another sort of sidecar file to the scene. That's the ANG file that contains information that will allow us to get the actual footprint of the STAC item, because a STAC item has a bounding box which is aligned with the coordinate reference system. But the geometry of the STAC item should represent the actual footprint of the assets contained inside of that item. In this case, the Landsat scene. And if you've seen Landsat, it's sort of tilted to the side of the in relation to coordinate reference system. So what we really want is the actual footprint of the geometry of the polygon of the footprint of that image. So this is the code that we'll use to get that. That uses the information contained in the ANG file and the bounding box to create a GeoJSON polygon that represents the bounding box. I mean, so the footprint. And so this is a good time, if you're following along, to sort of check to make sure that you got your initial coordinates right. So the way that I like to do that is to sort of print out, we can just like dump out the string of GeoJSON and then go ahead and use geojson.io to paste this in and make sure that the scene is, is in the correct location. And like I said, this is now a tilted according to like the UTM CRS that the assets are in, but also Web Mercator. These are sort of tilted, so it's not just a bounding box. It's a polygon, and you can see that Philadelphia is a little off the mark. But if we take the, it makes sense with the, if you take the bounding box of this footprint, it would actually contain Philadelphia. All right, so now we have all the required information to create the item, right? The properties is a required item, but it's fine to pass an empty dictionary, and we can sort of validate, or we can sort of hydrate the properties once we have the item actually created. And then so a newer feature of PySTAC is that we have a validate method that will reach out, grab the JSON schemas for the appropriate stack object that you're working with and validate it. So we can go ahead and validate the item. You can see that it returns the schema that it used to validate the item. So if I were to do something, let's go ahead and say that I created an item with a bounding box that with a string, and then go ahead and try to validate that. The exception messages are a little bit hard to parse, but if you look in the middle here, you're going to see that validating the type. Can people put themselves on mute? I'm getting a little bit of feedback. Yeah, so it specifies that the bounding box items should be type number, and the instance is no, so it specifies, oh, I messed that up. So let me go ahead and put that back, and we can see that again now. It validates. There we go. So along with the required properties of an item, we can add all the information that we have on a Landsat scene that is sort of extra. So there's this thing called common metadata, which specifies a lot of properties that, let me go ahead and see if I can get some help on that. A lot of properties that are sort of common to the STAC items, but not necessarily core. So we have things like license, we have platform, description, etc. And so one of these things is, is the ground sample distance. So I'll just, let's see if I can just do this. Yeah, that didn't really help. So the ground sample distance is just, you know, the resolution of the raster, so, or the assets. So most of the bands of Landsat are 30 meter. So we'll go ahead and set this to 30. They're not all 30 meter though, but we can handle that at the asset level, which you'll see later. Other information that's not in the core or in common metadata can be handled by extensions. So we're going to actually implement 3 extensions on these items, the first of which are the EO extension. So we're going to go ahead and enable that extension, and that allows, that marks the item as implementing that extension, and then allows you to access that extension through this ext class object that hangs off of the item. So what we're going to do first is just add the cloud cover from the metadata, which is just represented by this cloud cover key. And now we're going to add the assets of the Landsat scene. So I've created a dictionary here that just tracks information for each of the bands of Landsat, right? There's 11 bands, each with a key B1 through B11. And from the EO extension, there's a class called band that allows you to specify information about the band. And this all matches the spec. So if we were actually to go to the STAC spec, and look at EO, and go ahead and check out band, right? There's name, common name description, center wavelength, full width, half max. And these match exactly with the STAC spec. So one of the things we try to do with PySTAC is make sure that you know, the STAC spec serves as documentation for PySTAC, and then also if you work with PySTAC, it uses the same language and you know, the same model as STAC. So there we go. So we define a band for each of the B1 through B11. And then also mark the ground sample distance for each band. And like I said, most of them are 30, but there is a pan band that is 15 and a couple that are 100 meter ground sample distance. There's also some other assets, including the MTL and ANG file that we've already worked with. So I'm just recording in a dictionary that's returned per scene of, excuse me, of the media type and the href for each of these. Includes a thumbnail, the home page, and then also a geotiff that is a QA band. And this is sort of a question for the audience. Is the QA band a cloud optimized geotiff, or is it a straight geotiff? Because I marked it as a geotiff. Does anybody know? Either way, you know, if your assets are cloud optimized geotiff, it's best to mark it as a cog explicitly. But geotiff works for either. You know, a cog is a geotiff, so this would ring true even if the QA band was in fact a cloud optimized geotiff. So armed with this information, we're able to iterate through all of the band info items. We basically get that asset URL for the band ID for the TIFF. We go ahead and create a PySTAC asset that has that band URL and specifies the media type as a cloud optimized geotiff. We're going to go ahead and grab the band. So the band property is a list of bands because, you know, a geotiff can have multiple bands. So we can specify a list here, but we only have a single band per file in this case. We're going to go ahead and set the bands on the specific asset since each asset has a different band. If I were to do this, it would set the band on the item, which would represent, you know, item-wide bands, which you can do with the EO extension. But in our case, we have a band information per asset, so we'll set it right on the asset. And then we'll go ahead and add the asset to the item. And here's where I say, you know, if the band information ground sample distance is different from the common metadata ground sample distance, go ahead and set that right on the asset. So it defaults to the item's ground sample distance if it's not supplied, which is 30. And then if it has one that is 15 or 100, it'll set it directly onto the asset. And in this loop, I'll just add all the other assets like the thumbnails based on their ID and you know, the information, the media type and href that we supplied above. Go ahead and run that. And then we'll just see what a sort of JSON representation of each of the assets looks like for the bands. So band 10, you can see that the ground sample distance is specified along with the EO bands data. And then for band 3, which has a ground sample distance of 30, that is left out. And then for just to show a non-band asset as well, we have the thumbnail, which doesn't include any of the EO information because it's not applicable. So now we can add our other extension information, right? So each Landsat scene has a CRS, coordinate reference system that can be represented by the EPSG code. So this method just gets the EPSG code based off of the center latitude location of the scene and this UTM zone property. So we'll go ahead and enable the projection extension and then set the EPSG appropriately. And there's also an extension called view geometry, which talks about the angles of the sensors and the sun when the scene was taken. And so Landsat scenes are supplied with a sun azimuth and sun elevation. So we'll go ahead and set that by enabling the view extension and then setting the appropriate information. Excuse me. And at the end of the day, you can see that our item properties are now filled out with information from 3 different extensions, a common metadata field, and then here's our datetime that we specified in the construction of the object. Now that we have all the information, I can go ahead and validate. And now you can see that the schemas that are applied to the item are now from the item spec, but also for each of the 3 extensions that were enabled. So now we know, okay, this is now valid for all of the extensions and core stack that this implements. So we're going to go ahead and build a stack collection to house all of these items. Collection is a subtype of catalog. So a collection is a catalog, but specifies more information. So we'll go ahead and look at what we need from a collection in order to satisfy this, right? We need an ID, description, and an extent. We can go ahead and give it a title too. So for the collection ID, I'll just use that location name that we defined above. So if you change it, it'll be different on your machine. Give it a simple title. And then the description can be written as Markdown. So I have a little bit of Markdown just to show, and in the stack browser, we'll see that that Markdown is rendered. You know, if this is a real stack, definitely encourage folk to put a lot of time into the description to make sure that you know, folks know that what the stack is and how to access things and what they're dealing with. The extent is a combination of a spatial extent and a temporal extent. So it describes the spatial footprint or the spatial bounding box and the time interval or intervals that the collection is valid for. So for right now, we're just going to define a global spatial extent and then a datetime that starts with the first scene contained and then is unbounded at the top, and set that extent. So now we can create the collection with all the properties that we defined above. And if we look at it to dict, right, that just kind of converts it to its JSON form. We can see that these are all set in the proper places. And you can see that the links are there. There's a root link, but the href is none, right? So we've been working with these stack objects in memory and haven't specified their file locations yet. So we can do that a little bit further down. First off, though, this license is proprietary. So the default license is proprietary. But thankfully, Landsat is not proprietary. So we'll set the SPDX string for public domain on the collection. We're also going to set the non-required property, which is providers, by filling out the information from these provider objects, right, which just specifies the name of the provider, the roles that they the roles that they played in providing the data, and then a URL that can be displayed as a link to properly credit those who have created the data. And so now I'll just take all of the things that we did above to create the item for one scene, and then just kind of consolidate it into a single function that takes a scene and then reads in the metadata, gets the bounding box, creates the item, sets the geometry, etc. You know, fills out the EO information, projection information, adds the assets, and then goes ahead and validates it. It's just, I'm sorry, just to make sure that we, you know, got things right. And then for each of our location scenes, those 52 scenes, we'll add the item to the collection. This is going to take a little bit because it's reaching out to the internet, grabbing the MTL and ANG files. So real quick, I'm just going to look at the STAC browser, which we'll be using to visualize this data. So STAC browser is a view-based project that can visualize static stack catalogs. And so if you're following along, you want to run this, I'd recommend going through the running section. It runs through Node. And basically, if you supply a catalog URL and start up a server, you'll be able to view a stack catalog through the browser. And it defaults now to the latest version, which is 1.0.0 beta 2. But you can set a specific stack version, and it will read the stack version from the catalog to display the appropriate version. All right, so that is done. So we're gonna now use a cool method that was actually contributed to PySTAC in the last tooling sprint by a new contributor called update extent from items. And basically what that does, is, so it seems like that install didn't quite work because that function should be available. But basically what this would do is crawl through the items of the collection and we crawl through the items of collection and set the extent and the temporal intervals based on the items extents and the items time intervals. So I'm just gonna real quick go to the API reference to the collection and show that this function exists. So I'm not sure why it's not showing up in my notebook right now, but hopefully it will work on your machine. Great. So last thing I'm going to do is set the HREFs for everything in the catalog, right? So like I said, we're working, we have none for HREFs and everything because we're working in memory. So I'm just going to use the normalize HREFs to normalize everything to the catalog layout that is part of the, that is sort of laid out in the best practices document for STAC. So all I have to do is give it a root directory, which I'll just use the user's home and then the location name Landsat STAC, and then go ahead and set all the HREFs for the catalog. And then, yeah, for some reason this installed the, oh, because I think when I installed the, I think when this ended up failing, it installed 0.5.0, so there's a couple of functions missing. Apologies for that. But the validate all will just crawl through a catalog and use the validate methods on each of the STAC objects and encounters to make sure that everything is validated. That was introduced in 0.5.3, I think. All right, so last thing we're gonna do is to go ahead and write the catalog locally. In the best practices documentation, it describes a few different, let's see if I can get it to show. No, okay, so yeah, a few different catalog types. Absolute published is a stack catalog in which all of the objects inside of the catalog will have a self link that will point to an absolute URL of the item, and then also all link HREFs are absolute links. So that's really good for if you're publishing a catalog and it's not going to move anywhere. It's like that once, that's the like sort of definitive version of it. There's also relative published, which has relative links for everything and no self HREFs instead of, except for the root catalog, which has its published HREF. And then self-contained is one that has no self HREFs and all relative links. And it's really easy to sort of take a directory, move it around, and continue to have a valid stack. So that just saved based on all the HREFs that we just set and to our local machine. And then, so now that we wrote out the stack, there's like, you know, you probably want to see what happened. So there's a couple different ways to look at things, right? We can use this describe method that just kind of gives like a simple text-based representation of the stack. We can also like go through and like say to dict on the various stack objects. You can see all the links here, but staring at text is boring. So what we'll use is the stack browser tool. So the stack browser tool does not work off of like local file paths. So what I'm going to do here is actually change the directory, my working directory, to the root path of the catalog, and then set up a simple HTTP server to listen to port 5555 and serve stuff out. And then this, you know, it's important to enable CORS for when you're serving out a public stack, or if you're serving out a stack, because otherwise you'll get CORS errors in your browser. That will be annoying. But let's go ahead and use this server. And then now I can use Stack Browser to look at this stack. So if I go ahead and go over here, basically what I'm going to do is just like the README in the Stack Browser says, I'm going to set the catalog URL equal to HTTP localhost 5555. And then because it's a collection, right? It's a collection.json, not catalog.json. And then I'm going to say npm start. And so this should start up something at this location. Once it's done building, I can go ahead and open this up. And here is my Philly Landsat 8 catalog, which I can, you know, start to browse through. This pulls from the tiles.radiant.io method to render it on an interactive map, which is really awesome. And then I can see the thumbnail and, of course, all the assets. We can see our view, geometry, projection, and EO information here. So that's, I think I'll stop it there. You know, we've seen how we can start from some Landsat with some metadata, subset it, build a static stack catalog locally, and view it with the STAC browser. So hopefully that was informative, and I'll stop here, pause here for any questions.
So I guess I've got one. Looking through here, I'm still somewhat new to this. So I'm kind of trying to follow, but did you download the TIFFs locally and then kind of reload them as a stack, or is it just kind of like you're really just pointing to them in storage?
We're really just pointing to them in storage. So for instance,
Yeah. Okay.
Yeah, so if I take, you know, I have my item here, if I still have it up. So as I'm serving, I have to actually interrupt the kernel to get back control. So we have this item, and if I say item, let's say item assets, right? This will list out all of my assets, and you can see that all of the HREFs are still the remote locations. So I haven't downloaded any actual data. I've just created metadata that points to the cloud data.
Okay. And then if I were to like, say I wanted to like upload my own TIFF that would just be added to this catalog, would I just rewrite the catalog at that point, or is there a way to like edit it, I guess?
Yeah, so you could say, let's see if I can figure out how to do this real time. Let's get self href. So this is the location of the collection on disk. So if I were to say like collection 2 equals PySTAC.read file and give it that, now I have that collection again. And then so say if I had a new item that pointed to, we'll just pretend for now. If I had an item that had that new information, I would just say call2.add item, and then I could save off this collection again. Now currently it will rewrite the catalog, which is not super desirable for updating static catalogs. In the future, it's going to be a little bit smarter. You can actually, so for a collection, if you say save with the catalog type, it'll recursively save through a catalog, but every stack object has a save object on it, which will actually just save off. Yeah, so I mean, this is none. So let's just add, I think I messed that up. Anyway, this would work. So if you if you save an object, it'll just only save that individual file. It won't crawl through the catalog and save everything. So what you could do is, like, if you updated the collection and you had a new item, you could call save object on the item, save object, add it to the collection, call save object on the collection, and then you're good to go. Does that make sense?
Kinda. I think for me, I need to get a little more comfortable with this, but I think yeah, I'm pretty new to this flow still.
Sure.
But yeah, that makes sense. Like generally, as far as adding them.
Right. So now I've sort of like duplicated an item 2, added it, and then called collection.saveObject, which only writes the metadata, that collection.json, and not anything else. But yeah, and this goes for everybody. If you have any questions about the flow, the spec, how PySTAC can be used, where its development's at, what, especially if you have feature requests, which are great, please reach out in the Gitter or write up a GitHub issue. It's really great to hear people's usage of PySTAC, and then also like ways they can improve and different use cases it can better support.
Sweet, thank you.
Mm-hmm. Awesome. So I think I'm at time. So one other thing is I just want to give an acknowledgement to the SAT STAC Landsat project, which I grabbed a lot of code from. That was written by my buddy Matt, who is going to be presenting next. So with that, I'll pass it to you.
Thanks, Rob. All right. So let me share my screen. One sec.